Good morning. Welcome to Bharat Institute of Higher Education and Research. Today we are going to discuss course parallel and distributed computing. Course code U18Pecs035. We are going to discuss about the topic synchronization in parallel programming. Myself, Bhaskar Dhanaraj, Assistant Professor, Department of Computer Science and Engineering, Bharat Institute of Higher Education and Research. Synchronization. When we talk about synchronization, we need to know why we need synchronization. How to synchronization. So, when we are doing serial computing, synchronization will not be a concern because the process will execute one by one at a time, and the instructions in the process will execute serially, one at a time. When it comes to parallel programming, synchronization is a typical problem that arises. Synchronization, how to synchronize processes, need to protect access from the shared data. Processors will access resources. The resources may be a hardware or file or maybe a software. In some cases, even maybe peripheral devices. For example, printers. To avoid the synchronization problem, we have so many mechanisms and algorithms. We have both hardware mechanism as well as software mechanisms. This synchronization will lead to deadlock and race condition. Synchronization mechanisms in parallel programming. One of the typical problems in building shared resources based parallel computing. When you are doing parallel computing, parallel programming, this synchronization will become a vital role, plays a vital role in your programming. At the source language level, these resources are mostly shared variables. At the machine language level, they are registers, memory cells, and status flags, etc. As far as parallel computing concerned, to improve the productivity and the confidence, source language should provide high-level abstractions for synchronization to ease parallel programming. Rather than simply providing logs, compiler and runtime systems are required to provide accurate and efficient implementation for such abstractions. How to synchronize? Need to protect access to shared data to avoid problems like deadlocks, race conditions. Deadlock is a circular wait condition. There is one process is waiting for another process in a circular or in a loop manner. Race condition is all the process are in a race to access the shared resources. We'll see an example. Updating a shared account balance. Here, two processors playing role in the same account balance. One processor trying to add the account balance, another processor trying to subtract some value, then account balance. So this makes a confusion if these two processes will not be synchronized. So to make these confusions clear, this processor and this process should execute one at a time. The next one is critical section. In general, n processors all competing to use some shared data. Each process has a critical section in which shared data is accessed. The goal of the critical section is to ensure that when one process is executing in its critical section, no other process is allowed to execute in its critical sections. Processor critical section has three sections. One is entry sections, where there will be an entry of a process, and critical section. As I said before, there will be only one process will be present in critical section, and an exit section, that is reminder section, which releases exclusively. There are some criteria for critical sections. That is mutual exclusion, progress, and bounded waiting. We'll see one by one. Mutual exclusion. That is, two processors can never be the critical section at the same time. So any one processor should mutually accept, so only one at a time. So no two processor never be in the critical section at the same time. That is mutual exclusion. The major criteria of the critical section is mutual exclusion. Another one is progress. If no process is executing in its critical section, and some processes wish to enter the critical section, then only those processes that are not executing in the reminder section can participate in the decision on which will enter its critical section next. So this is based on the process present in the reminder section. So the process present in the reminder section will get completed its work so that the next process can enter into the critical section. So that is the major idea behind progress sections. Bounded waiting. There exists a bound or limit on the number of times that other processes are allowed to enter the critical section after your process has made a request to enter its critical section and before that request is granted. So these are the three major criteria for critical sections. We have a mechanism for critical section. One is first attempt. It's an alternation mechanism where two processes trying to enter into the critical section, but there is a alternation tag. One is turn not equal to 0, another one is turn not equal to 1, which satisfies mutual exclusion but does not satisfy progress. It might satisfy bounded wait, possibly, not possibly. If processors eventually set the turn variable to 0 and 1. The second attempt is creating a warning flags. Two processors again involved to enter into the critical section. Here we implementing a flag which is nothing but of a warning flag, where flag of 0 equal to false, the processor 1 flag of 1 equal to false. So this satisfies mutual exclusion and progress. P0 only enters critical section if flag of 0 and not flag of 1. And when it comes to P1, processor 1 only enters into critical section if flag of 1 and not flag of 0. This satisfies bounded wait, but it may lead to deadlock possibly. Why? Because if these two processors trying to access processors, if the process are independent in nature, then we may get deadlock. Another mechanism which is called Peterson algorithm, software-based solution, where processor 0 shared a flag and the flag will be in the critical section, and which combines the alternation mechanism and flag mechanism. Want to enter, but if someone else want to enter, it should satisfy mutual exclusion, progress, and bounded wait. The slow, busy wait and unwieldy takes 10 many processes. This is an efficient solution. So because of the combination of previous two mechanisms, alteration and warning flags. Hardware-based synchronization. Hardware synchronization for large-scale multiprocessors. Hardware synchronization can be a bottleneck. Its contention adds additional delay and potentially great latency. Hardware primitives needed, that is all solution based on atomically inspect and update a memory location. The higher level synchronization solution can be built on the top of the basics of hardware primitives. That is locks, barriers, generally employed by the system software, not the program directly. Uninterruptible instruction to fetch and write to memory. That should be implemented in 3 ways. One is atomic exchange, another one is test and set, another one is fetch and increment. Interchange a value in a register for a value in memory. So there is a interchange, there is a swap occurs, use it to build a simple lock. To lock, set register to 1 and exchange 0. This synchronization variable is free 1. One synchronization variable is locked by some other process and unavailable. Must be atomic or synchronization and fail. Test and set. Test a value and set it if the value passes the test. For example, test for 0 and if so, set to 1. So test a value. If it passes the value passes the test, then set the value. So this is another mechanism. And final, fetch and increment. It returns the value of memory location and automatically increments it to 0. Synchronization variable is free. So all implementation requires coherence. Now, I'm going to see SpinLock. A SpinLock using the exchange primitive processes continuously tries to occur, spinning around a loop, trying to get the lock. If it is already locked, then multiprocessor with cache coherency want to spin on cache copy to avoid full memory latency. The problem is exchange includes a write which invalidates all other copies. This generates considerable bus traffic. And we have a solution for this to start by simply repeatedly reading the variable when it changes, and then try exchange. Load linked or store conditional. So LL or AC. Challenging to implement a single atomic memory operation has to do a memory read and a write, which complicates coherence. Since the hardware cannot allow any other operation between read and write, alternatively, have a pair of instructions, a load and a store. The second instruction returns a value from which it can deduce if the pair executed as if it were atomic. The load is special load called load link and load locked, and the special store is called store conditional. In short form, load link is represented as LL and store conditional is represented as SC. For example, with LL or SC, atomic swap with LL and SC on memory location specified by R1, move exchange value, load link, store conditional. So this branch store fails and put the load value in fails. The atomic fetch and increment, load linked, increment, store conditional, this branch stores fails again. Implementing load link and store conditional link register stores the address specified in the load link. Instruction, interrupt, or catch block matching the link register is invalid. It clears the link register. The same idea as snooping, listening for a write on the address of the link register. Some care must be taken. So deadlock condition possibly depending upon what is placed between load link and store conditional. Should only be register to register instruction. The next synchronization mechanism is In hardware mechanism, the next one is barrier synchronization. Barrier synchronization. So there is a condition that all must arrive before anyone can leave, used between different parallel sections. This barrier condition uses two shared variables. One is counter variable, another one is flag variable. A counter variable that counts how many have arrived. The flag variable said when the last processor arrives. In barrier synchronization, we have so many types. The first one is simple barrier synchronization, which is slow. When the two process fast and slow mechanism, fast arrives, set releases to true, goes on to execute other code, comes to barrier again, and reset releases to false. Start spinning on wait for release. Just slow to read and release again. It sees false again. Now both processors are stuck and will never leave. Correct barrier synchronization. Correct barrier synchronization has a local sense and toggle sense. So here, which releases in first barrier act as a reset for second barrier. When fast comes back, it does not change release. But just wait for it to become false. Slowly, eventually, sees release is true. And stop waiting, does work, comes back, sets release to false, and both go forward. Initially, the local sense is equal to false and release equal to false. Large-scale systems. Large-scale systems, the barriers vary with many processes that have to update counter one by one. It takes a long time for the barriers. The solution is to combine three of barriers. For example, using binary tree pair up processors, each pair has its own barrier. It synchronizes with one barriers. All the processors are in synchronized state. Just spin until the level the barrier is released. At the highest level, all processors will spin and a few representatives will be counted. Works well because each level fast and few levels. Large-scale systems locks contentions even with the test and set. Every write goes to many spinning procedures, which making everybody test less often or reduce contention for high contention locks, but it adds for low contention locks. So the solution is the exponential back off. If we have waited for a long time, lock is probably high contention. Every time we check and fail, double the time between checks. So the fast low contention locks and scalable high contention locks, there is a special hardware support needed. Memory consistency. Memory consistency. When does a processor see another processor's return value? So it do different processor see writes at the same time. If writes are immediately seen by other processors, it will be impossible for both if statements to evaluate are true. Sequential consistency. Sequential consistency is developed by Lampford in 1979. A multiprocessor is sequentially consistent if the result of any execution is the same as if the memory operation for all the processes were executed in some sequential order. And the operation of each individual processes occur in this sequence in the order specified by its program. So all processes see all loads or stores happening in the same order. Sequential consistency, simple implementation. A processor issues next access only when its previous access is complete. That is sequential, right? So one by one after another. Under this sequential consistency, we cannot place the write in a write buffer and continue. So sequential consistency is slow, but better performance. Latency hiding techniques, less restrictive memory consistency model. Relative consistency. Relaxed consistency models, synchronized programs. A program is synchronized if all access to shared data are ordered by synchronization operation. Any two of accesses to the same variable in two different processes such that at least one of the access is a write are always ordered by synchronization operation. If variables may be updated without synchronization, then data race and outcomes is unpredictable. The goal is data race free, good performance even in a simple implementation. Seems acceptable for programmers, accepted that most programs are synchronized and behave as if the hardware implemented sequentially consistent. Relaxed consistency models, there are many other relaxed models. Processor consistency, partial store order, release consistency, lazy release consistency, all work just fine for data race free programs. But when there are data race, more relaxed models wire program behavior. Thank you.